40 Days of Chemistry Part 2, and this time by request we're looking at 9.2.5, or part of 9.2.5, focusing on radiation, radioisotopes, and transuranics. And the first thing we're going to look at is the types of radiation and their properties. As we know, there are three types of nuclear radiation. They're called nuclear radiation because they come out of the nucleus. And the first of them is alpha radiation. Now, alpha radiation is a helium nucleus. It's got a mass of 4 because it consists of 2 protons and 2 neutrons, and it's got a charge of 2+ because it contains those 2 protons. The next type is beta radiation. It's a high-speed electron coming out of the nucleus of an unstable isotope. It's an electron, so its symbol is E. It's effectively got no mass, and it's got a charge of -1, hence its symbol is 0, -1e. The third type of nuclear radiation is a gamma ray. It's a high-energy EM radiation beam coming out of the nucleus. Because it's radiation, it's EM radiation, it's got no mass, it's got no charge, its symbol is 0, 0, gamma. Now, all these types of radiation are called ionizing radiation, and what that means, we know in chemistry, ionizing means losing electrons, or gaining electrons. In this case, it's losing electrons. When radiation comes into an atom, if it strikes the atom, it can give its energy to one of the electrons in the atom, and that causes the electron to actually leave the atom, or the atom is becoming ionized as an electron leaving. In the process, that radiation usually stops because it's dumped all its energy onto the atom, ionizing the atom. Why that's dangerous is because that atom might be part of a cell, in particular it might be part of a molecule in a cell, and that electron that's been lost might have been part of a covalent bond, and once that electron's gone, that bond is broken. So here's radiation coming into a cell, it's striking part of the cell, in this case a segment of DNA. Because the bonding is broken, because the atoms have been ionized, the DNA is broken, that means the DNA is mutated, that could lead to the formation of a cancer cell and a tumor, hence ionizing radiation is very dangerous. However, not all these radiations have the same ionizing power. Because alpha particles have effectively very high mass and charge, they've got a mass of 4 and a charge of 2, they readily ionize. They'll basically ionize the first atom they hit. And because they ionize the first atom they hit, that means they don't penetrate very far. So if an alpha particle is coming in towards paper, it'll ionize the first atom it hits in the paper, and therefore it will stop. Therefore it's got very high ionizing power but very low penetration power. Beta particles have less mass and less charge, therefore they've only got moderate ionizing power and moderate penetrating power. They can be stopped by things like aluminium. Finally, gamma rays, because they've got no mass and no charge, they don't readily ionize atoms. They usually pass straight by them or pass straight through them. However, they can be stopped or partially stopped by things like that. They've got low ionizing power and high penetrating power. And the other diagrams on the page are just nice little diagrams illustrating what happens in alpha, beta, and gamma radiation. Now, why do some isotopes emit radiation? Well, they're radioisotopes, which mean they're unstable, and it's all to do with something called the line of stability. Now, the line of stability, it might be hard to see in this diagram, is this middle line. It's this black line in between the blue and the orange regions here. And what that line of stability represents is the isotopes that are actually stable. This graph here shows number of neutrons versus number of protons. All the coloured dots represent known isotopes. For example, up here, this would represent an atom with 28 protons and 126 neutrons. No such isotope exists. There's no such thing as 28 protons, 128 neutrons, but there are things in this coloured region here. They're the known isotopes. However, only some of them on that line of stability are stable. And why that is because, as we know, the nucleus consists of a whole lot of protons very close together. But protons are positively charged and don't want to be together. They actually have an electrostatic repulsion pushing them apart. However, there's another force that exists inside the nucleus called the strong nuclear force. And the strong nuclear force exists between protons, neutrons, and neutrons and protons. And therefore, the more neutrons you have in the nucleus, the more of the strong nuclear force you're adding without adding any extra electrostatic repulsion. And therefore the neutrons effectively act like glue holding the nucleus together. And for very, very heavy elements, such as up here with, say, 82 protons, you've got a lot of electrostatic repulsion from all those protons in there. Therefore you need lots and lots and lots and lots of neutrons, which is why this line of stability deviates from this other line here. This other line represents the situation where you've got neutrons equal to protons. And for very small elements down here, the number of neutrons and protons are roughly the same. You need 1 neutron for every proton. But as the atoms get more and more and more protons, therefore there's more and more and more repulsion inside the nucleus, you progressively need more and more and more neutrons in there, more neutrons and protons to hold the nucleus together. Hence this line deviates away from that neutrons equals protons line. But what are the rules as far as the HSC is concerned for stable isotopes? Well, first of all, if the atomic number is bigger than 82, they're alpha emitters. And as you can see, here's the 82 line. If we draw that up here, pretty much everything on this side is yellow, which means they're alpha emitters. And that's because once you've got more than 82 protons in the nucleus, there is no number of neutrons you can add to make it stable. There's just too many protons, there's just too much electrostatic repulsion, and therefore those nuclei will always spontaneously decay, producing alpha particles. And there's an example here, e.g. 23892, its atomic number is 92, that's bigger than 82, therefore it's an alpha emitter, so we know it's going to turn into an alpha particle, or 42He, and just by simple mathematics, the top line must line up, so that must be 234. The bottom line must line up, making that 90, and therefore it's going to turn into an alpha particle and thorium. Note, in alpha emission, the atomic number drops by 2, and the atomic mass drops by 4. Beta radiation. If you've got too many neutrons, or the neutron-proton ratio is too high, that means you're going to be a beta minus emitter. If you've got a too low neutron-to-proton ratio, which means you've got too many protons, you'll be a beta plus emitter. That still hasn't shown up in the HSC. I'm not sure it's part of the course, but just in case, I'll let you know here. And that's represented by these blue and these orange regions here. The blue regions are above the line, hence, i.e., too many neutrons, therefore they're beta minus emitters. The things below the line mean not enough neutrons or too many protons, therefore they're beta plus emitters. As an example, carbon-14. Well, how do we know that's a beta emitter? We can look down here. The stable ratio is neutron protons. If you've got less than a 20 atomic number, you should have 1 neutron for every proton. If you're at atomic number 50, you've deviated from this line a little bit. See, the line is deviated there. You need about 1.3 neutrons for every proton. If you're atomic number 80, which is about here, it's deviated even more from that line, you need 1.5 neutrons for every proton. So carbon-14 here, because its atomic number is less than 20, you should have 1 proton for every neutron. But in this case, how many neutrons we got? Neutrons, as it says down here, are the atomic mass take away the atomic number. It's going to be 14 take away 6. This has got 8 neutrons. But it should have 1 to 1. It's got 6 protons, 8 neutrons. Too many neutrons, it's a beta minus emitter. So let's put that beta minus in. It's going to give off an electron, 0 minus 1 E. And if we do the mathematics, the top number's got to be the same. The bottom number, this number, take away 1, must equal 6. It must be 7. So when carbon-14 gives away its beta particle, it turns into nitrogen-14. Note, in beta emission, the atomic number actually rises by 1, but the atomic mass doesn't change. And an example for you should go ahead and do these to make sure you understand how to calculate number of neutrons and a neutron-to-proton ratio. Finally, if the nucleus contains too much energy, it's called metastable. That usually happens after it's given off alpha or beta particles. It's called a gamma emitter. For example, technetium-99m, it's got too much energy in the nucleus. It gives off a gamma ray. It doesn't change though, it stays as technetium-99, it's just that it's no longer metastable. Now, note, this doesn't change element, it's still technetium, and therefore gamma decay, it is a type of radiation, but it's not a transmutating radiation. These two types of radiation, alpha and beta, they cause transmutation. I.e., you have one element turning into another. But let's move on. If we can. No, it doesn't want me to move on. Quick, let's move on. What is a nuclear reactor? Well, this is where we make some of our radioisotopes. You can pause it here and read all about reactors. The key idea is that fission reactors or nuclear reactors are one of the few places you can actually get high-speed neutrons. And high-speed neutrons are needed to manufacture neutron-rich beta-emitting isotopes. There's an equation here you should be able to fill in. This is a fission equation. You should be able to figure out what that equation is by filling in the numbers. Let's move on. The other thing we need to understand to make radioisotopes is particle accelerators. Basically, particle accelerators are huge devices that use electromagnetic fields to accelerate charged particles. They basically accelerate charged particles and smash them into each other. And particle accelerators are very important for manufacturing proton-rich beta plus emitters and also heavy transuranics. And as you can see, this is a medical cyclotron to make medical isotopes. This is a big particle accelerator used to make transuranics, and this is the massive LHC particle accelerator used to investigate the early universe. As you can see, the bigger and bigger and bigger the particle accelerators gets, the higher and higher speed you can accelerate your particles. So how do you make commercial radioisotopes? Well, you need to know what an isotope, a radioisotope, and a commercial radioisotope are, and that's put up here. But there's two ways you can make commercial isotopes in a nuclear reactor. First of all, sometimes the fission products from nuclear fission itself are useful radioisotopes. So when uranium-235 as a nuclear fuel undergoes fission, it can turn into molybdenum-99. One of the daughter products can be a useful radioisotope. The other way you can make useful radioisotopes inside a nuclear reactor is that you can bombard stable isotopes with the neutrons in the nuclear reactor. For example, that's how they make cobalt-60. They get stable cobalt-59, they smash a neutron inside it becomes cobalt-60. You can also make commercial radioisotopes in a particle accelerator by accelerating small charged particles into other atoms. That's how they make fluorine-18 for PET scans. I guess that was a bit too long, 10 minutes rather than 5 minutes, but we've got to continue anyway. How are transuranics made and what are they? A transuranic is an element with atomic number bigger than 92, and because they've got atomic number bigger than 92, that means they're unstable, because we know that all elements with atomic number greater than 92 are unstable, and we can assume in the HSC course that because they've got atomic number greater than 82, they're all alpha emitters, unless you're told otherwise. The way they're made is this almost exactly the same as how you make commercial radioisotopes. You can make them in a nuclear reactor, and you can make them in a particle accelerator. In a nuclear reactor, though, what you do is you bombard uranium. Now, the fuel we use in a nuclear reactor is usually uranium-235, which can undergo fission, which means split and give off more neutrons. But if you put non-fissile uranium-238 inside a nuclear reactor, it'll absorb the neutrons rather than splitting when neutrons hit it. That means it becomes a beta emitter, and when it's a beta emitter, it gives off a beta particle and turns into neptunium-239, which is the first transuranic. Neptunium-239 will then undergo beta decay itself to produce plutonium, which is the second transuranic. That's plutonium can then absorb 2 more neutrons because it's still inside the nuclear reactor, absorbing neutrons to become plutonium-241, which will then undergo beta decay to produce americium-241. So you can actually make neptunium, plutonium, and americium just by putting uranium-238 inside a nuclear reactor, and they're the first 3 transuranics. However, if you want to make transuranics with atomic numbers bigger than 95, you have to use a particle accelerator. And what they do is they accelerate heavy ions, such as calcium ions, into heavy metal or transuranic targets to make heavy transuranics. So just like a commercial radioisotope, you can use a nuclear reactor or a particle accelerator to make transuranics. And in part of the course, you have to actually know some recent discoveries of elements, and they've all been discovered in particle accelerators. And what they do is they bombard, over time anyway, they've bombarded larger and larger ions into targets, and what they get is they get heavier and heavier transuranics. But as they get heavier, that means you've got more protons, which means you've got more electrostatic repulsion, which means they become more and more unstable, and they've got shorter and shorter half-lives as we go on. But in 1998, scientists at Dubna in Russia discovered fluorovium. And when they did that by getting a plutonium target and putting it inside the particle accelerator, they got the calcium ion and used the particle accelerator to speed it up to very high speeds. They smashed the calcium into the plutonium, and the calcium and plutonium nuclei merged to become fluorovium. In a very similar technique, in 2000, they did a very similar thing in Dubna again, but this time they smashed calcium ions into curium atoms. So they had some curie atoms inside the accelerator. They accelerated the calcium to very high speeds. They smashed the calcium into the curium, and that turned into livermorium. The reason it was called livermorium was because Lawrence Livermore Laboratory in America was their partners in making these particular isotopes. They were discovered very, very similar times. Around the same time, they also claimed to have discovered element 113, which is currently called ununtrium, is the sort of standard placeholder sort of name, but there was no conclusive evidence. But just last year, in Riken laboratories in Japan, some scientists did produce produce element 113 with pretty significant evidence. It hasn't been officially recognized by IUPAC yet, but if it is, they'll get the chance to name it. And the 3 names people are bouncing around are japonium, ricenium, and nishinanium, which is named after a famous Japanese physicist. And the way they made that was they accelerated zinc ions and they smashed them into a bismuth target to make UUT, and we also released 1 neutron. So that's recent discoveries of the elements. And now finally, that is the end of our supposedly 5 minutes a day chemistry.